Now let's develop here the equation for the horizontal shear which is due to the bending stress. For this purpose we'll consider here one single plank and the cross section of the plank is shown here. We'll take here the variable width from top to bottom. At bottom we have a flange. So maximum area is on the bottom side. So centroid will be on the bottom side. Let represent G here, which means the centroid. So number of loads are acting on this plank and we can develop the shear force and bending moment diagram for the given loading. We want to find out here the value of the shear stress at a fiber which is at a distance equal to y1 from neutral axis. Let's say we are considering the fiber at this location. So this one is a fiber that we are considering and this fiber at a distance of y1 from the neutral axis. We'll consider here a section of this beam. Let's say we have a section at somewhere here at a distance equal to x and this section is taken between the section plane A and B and these two section planes are separated by a small distance equal to dx. So let's say we have a bending moment at the section plane A will be equal to m and at B we have m plus dm. That is, we are assuming here the bending moment is changing continuously from A to B. The dm value can be positive or can be negative, that is the bending moment can increase or decrease, that we don't know. Temporarily we assume the value of dm is positive, that is dm is greater than 0. That is, we assume here that the bending moment from A to B will go on increasing. So we have to show here one bending stress distribution for section at A for the given cross section. The top fiber here is away from the neutral axis, so maximum bending stress will be developed. Let's assume as a tension and is a maximum on the top fiber. In that case, at the bottom we have compression and the distance of the bottom fiber from the centroid is less as compared to the top fiber, so we have less value of compressive stress. So at section plane A we are getting the bending stress distribution here. We have a tensile stress and this stress is maximum on the top fiber, compressive at the bottom fiber, which we have shown the lower value. Similarly, distribution we will get at the section plane B also, and since we have taken the value of m plus dm is more than m, so the larger value of the bending stress will produce as compared to A on the top fiber and the bottom fiber, because the bending stress is directly proportional to bending moment m. So this distribution you will get at the section plane B, and these two planes are separated by distance equal to dx, same as equal to dx. Suppose here the value of VA, that is the shear force at A, is not equal to 0 and even the shear force at B is not equal to 0. In that case we have a different bending moment act at A and B. Now here for A and B the shear force equal to 0, so we have same value of a bending moment. Right now if you observe C and D, we have shear force exists and is non-zero value. So for C we have bending moment is equal to m, and for section D we have bending moment is equal to m plus dm. So this variation we have taken. Either you can take CD here or you can take CD here. If you take a CD here, the bending moment will go on decreasing from C to D. So that is the value of dm will be negative if you take on the right support, and here the value of dm is positive if you take at the left support. For the given loading here, we assume the shear force at A and B is not equal to 0. If the shear force is not equal to 0, then the bending moment will produce. Depending upon the value of dm is positive or negative, there is push or pull will take place between the two sections. So we'll consider here one section above the fiber at which we have to calculate the shear stress. That is above the fiber y1, we'll consider this hatch area. So all these stresses multiplied by the corresponding area will exert a force in a rightward direction. Let's say this total force here will be equal to Fa, and on the right hand side here at section plane B we have the total force equal to Fb, and this value of Fb will be equal to Fa plus a difference of force that equal to dF. Now we want to calculate here what is the value of Fa, what is the value of Fb, and how to calculate the value of dF. To calculate the value of FA here, we'll consider here one fiber at a distance equal to y from the neutral axis, and let's say the corresponding stress is equal to sigma. This stress we can calculate using the flexure formula, and we have flexure formula is sigma. The stress at distance y is equal to m multiplied by y divided by the moment of inertia I. And let's say the stress is acting on a small area here. So this one is representing here a small area. Let's say this area is equal to dA area. In that case, we can calculate here the force as a product of sigma multiplied by dA. So we have dF will be equal to the stress sigma multiplied by area dA. And to calculate the total force here, we have to integrate from y1 to the top distance, that is over the area. You have to integrate this. So this time we have dF is same as equal to m multiplied by y divided by I multiplied by area dA. Now the bending moment is remain constant over the section here. So we have total force FA will be same as m is a constant here, I is a constant here, y is variable, so we have y dA. And since we are integrating with respect to dA here, so you have to take the area FGHI. So this one is same as the area FGHI. Now this force is acting on the rightward direction. Similarly, we can calculate the value of FB on the similar basis. Only thing that at section B, we have bending moment acting is equal to m plus dm. So at this section, we have bending moment is m, and at this section, we have taken the bending moment equal to m plus dm. So we have the net force acting at the section plane B. FB will be equal to m plus dm divided by I, that is a bending moment, multiplied by integral y dA. And we have the same area, that is the hatch area, that equal to FGHI. Naturally here, because of m plus dm, FB is supposed to be the higher value, and difference between the FB and FA will denote as dF. So I will write this term two times here. First term I will write as m by I integral y dA, and we have same area, that is FGHI, plus we have dm divided by I integral y dA, and we have same area again, that is we have area FGHI. So this force dF must act in a rightward direction. FA is acting rightward, so somewhere we'll show here this force. This force is same as equal to dF. FA plus dF will be same as equal to FB. So we have dF is equal to FB minus FA. So this one is equation number 1, which is representing FA. This one is equation number 2 representing FB. So we have FB minus FA. So first term will be get cancelled, and we get the value of dF is equal to dm divided by I integral of y dA. And you have to do the integration for the area, that is equal to FGHI. Now if we apply the first moment of area, we know that the integral y dA is same as equal to area multiplied by y bar. Integration is done over the area FGHI. It means that this area is same as equal to the area FGHI, and this one is the centroid of the given area. So y bar represent here the centroid of area FGHI. So this hatch area I am showing separately. This one is our neutral axis NA. This one is our centroid equal to G. Our hatch area is FGHI. So you have to take this area and you have to locate the centroid of this area. Let's say that we have centroid is somewhere here. Let's mark this centroid equal to G1, and from neutral axis we have to measure the distance of this centroid, that is the hatch area, which one is above the fiber Y1. So this centroid at a distance equal to y bar, that is this term is y bar, centroid of the area FGHI. So you have to take all the area from this fiber up to the top. So that area will be equal to area AFGHI, and you have to take the centroid of this hatch area, that is FGHI. You have to record the value of y bar. In that case, we can calculate the value of df. So we have df is equal to dm by I, dm divided by I multiplied by the area FGHI multiplied by the centroid distance of the given area FGHI from the neutral axis, that is y bar. So this force dF here represents the longitudinal force in a distance dx. Now we'll develop here the three-dimensional figure for the section AB. At A we have the same section that is shown here. At B also we have a same section. These two sections are separated by distance equal to dx, and perpendicular to this plane we have the net force acting is dF. So this one is representing our section A, this one is representing the section B. These two planes are separated by distance equal to dx. This point is representing the centroid point on the plane A. This one is representing the centroid on the plane B. This one is representing the neutral axis. Somewhere we have taken the plane at a distance equal to y1 from the neutral axis. So this one is a plane here, and this plane has a length equal to dx, and it has a width equal to b at a distance equal to y1. So let's say the given plane at a distance equal to y1, we have width is equal to b. This point is same as f, one is g, one is h, and I. The force F is acting parallel to this plane, so this one is our force equal to dF. This force is parallel to the given area. Let me call this point as F prime, this point equal to G prime, H prime, and I prime. So the bottom plane form here is F prime, F, G, G prime. On this the force dF will act, and the area of this plane is same as equal to dx multiplied by width b. That will be called as the shear stress. So the given force F is parallel to the plane FG, G prime, F prime, and this plane has an area is equal to dx multiplied by width b. So area of the plane will be equal to dx multiplied by width b. Just to avoid the confusion about the area, what we'll do here, I will introduce here one term that is called as Q. Let me say here that this product here is equal to Q. So in this case we get dm multiplied by Q divided by I, and we have Q equals to same as area of the hatch area, that is this hatch area. Which one is F, G, H, I, and y bar is a centroid of this point, and this centroid from the neutral axis at a distance equal to y bar. So product of area of FGHI multiplied by y bar is replaced by Q. So we have dF equal to dm into Q by I, where Q is equal to area multiplied by y bar. So dF it is acting parallel to the plane, so that will develop the shear stress. So we have shear stress equal to 2 is dF divided by this area. Let's substitute here for dF. We have dF is equal to dm multiplied by Q divided by I. So we have dm divided by Q divided by I. The area is same as dx divided by b. So b I will write here, and I will club this term dm by dx because this term is familiar to us. So there exists a relation between the shear force V and bending moment M, and we have derivative of M with respect to x is same as the shear force V. So we'll use this equation. So this value of dm by dx is replaced by V. In that case we have shear stress tau is equal to dm by dx is same as V. So in numerator we have V into Q divided by I, that is the moment of inertia of an entire cross section, multiplied by width b at a distance equal to y1, where we are interested to know the shear stress. So your b is the width at the given section, and q we can replace as the area multiplied by y bar. So in general this formula is shear force V multiplied by area multiplied by y bar divided by I divided by the width at that section. In this case, the area is FGHI, which is nothing but the hatch area, which one is area above the Y1 up to the top fiber. And if you are interested below, then you have to take the area of that fiber up to the bottom fiber. The fiber represents here the distance of the centroid of the given hatch area, which one is FGHI, and the B here represents the width at a distance equal to Y1 from the neutral axis. So finally we have developed here the shear stress formula is same as the shear force at that section, and where you are interested to know the value of stress, so you mark that distance from the neutral axis either above or either below. If you mark it above, then take all the area above that fiber up to the top fiber. If you mark it below, then you take all the area below it up to the bottom fiber. Then B represents here the width at that distance equal to y1 from neutral axis, and y bar represents the area of the hatch area. In this fashion we can calculate the shear stress. I will explain the procedure how to find out the shear stress one more time. Whatever the section is given to you, first of all you have to locate the neutral axis. Let's say we have this section and we have located the neutral axis and we have centroid equal to G. We are interested to find out the shear stress at a distance equal to y1. So let's mark here this fiber, and we are interested to know what is the shear stress at this fiber. So let's mark here this distance equal to y1. Whatever the fiber you get, you take the fiber above the G, then you have to hash the area above it. First thing, you have to locate here the distance y1 at which we are interested to know the shear stress. Hash the area from this fiber up to the top fiber if we are above, and if we are below, then you have to the area from that fiber up to the bottom fiber. Once you know the area, that is, let's say this area equal to A, B, C, D, then you have to find out the centroid of the area. So you have to find out first what is the area A, B, C, D. Step number 2, find the centroid of this area. So you have to find out here the centroid of the area A, B, C, D. Let's mark this centroid equal to y bar. We can locate the centroid here somewhere equal to G, and this distance you have to mark as equal to y bar. This is the area A, and at this B we have taken for the width. So I will just change the point here B. Instead of B I will make it E. So let's take this area instead of A, B, C, D, because B is repeated here. A, E, C, D. So we have area is A, E, C, D. So you have to locate here the area A, C, E, D, and you have to mark the centroid equal to y bar. Then the given area is A. In this fashion our numerator is solved. Then what is left is width. So at this distance here y1, you have to measure the width, that equal to B. Final step is to measure the width at a distance equal to y1 from the neutral axis. So V is known, I is known, area is known, y bar is known, B is known, so we can calculate here the shear stress. Now one question is to answer, if the section is circular, rectangular, triangular, then how the variation of the shear stress will take place. So that distribution will take in the next video. So in next video we are going to discuss the distribution using the above formula of a shear stress. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.